Hello, and thank you for joining me. You're here with data science teacher Brandon, and we're going to go over how to build a convolutional network with the sequential model in TensorFlow. Okay. So importing some of our standard data science libraries. I'm also going to use the tf.keras import layers, make it a little bit easier to write our code in today. Okay. So in order to CV2, just a little bit of data exploration, just look at our images today, and PLT as well to help us look at our images, or sort of matplotlib, pyplot. Okay, so I'm just importing a reduced version of the MNIST dataset in CSV format in a data frame. It makes it pretty easy to work with. This is only 20% or 30% of the images from the full Kaggle competition. And so it's a small version, but it works for our purposes today. So just exploring our data sets, going through a loop here and using the plt.subplot to add different plots, kind of every number in each one of these plots. So you can look at each one of the digits, and I really like this plt.subplots function just because it allows us to say we want a grid 4x3, 4 rows, 3 columns, and then we're just going to say put it in place 1, place 2, place 3, and put this plot in each of the given places. Okay. And then just plt.tightayout again to make everything. It basically just make things tighter. What it essentially does is just reorganizes all the plot layouts, especially when you're adding multiple plots to this grid, this background. You can get a little jumbled around, so it's kind of clean stuff. Okay. But that's not what we're here to talk about. We're here to talk about our convolutional networks. So here what we're doing is just a little bit of pre-processing right here. So I'm going to take the data frame. I'm going to start from I'm going to take all of the rows, comma 1 to the end. So it's taking all of the columns except for the first column, which is the label. I'm going to reshape this. I'm saying ignore the number of rows, and then the rest of the dimension, reshape it, which would be one long dimension of 764, or 760, yeah, 764. And so what it's going to do is we're going to shape that to 28 by 28, okay? And then what it's going to do is we're going to one-hot encode the target space. Is going to be 10 columns then of, it's target 1, it would be in there, and the rest would be 0, and so on. So one-hot encode for that. And that's how the model does the linear algebra, and specifically working with the categorical cross entropy. You want to put it into your model as a one-hot encoded vector. So here what we're going to do is we're importing our data set right here, seeing the sequential model, and what we're going to do is we're going to do tf.keras.model sequential, and inside we're going to put a list of our layers. So the kind of convolutional network, when they say this, it's really 2 convolutional layers, a max pooling layer, and then a dropout. This is kind of the classic convolutional block. And then we there's lots of little alterations on this that we'll explore today, but this is really the magic. This is the CNN part, but really there's a lot of flexibility. There's no set thing. This is only a CNN, a convolutional neural network. There are many situations. So just notice here, putting in filters of 16. And what this is doing is basically making 16 dimensions, like 16 pictures on top of each other. Then each one of those planes, each one of those filters, those dimensions, will capture one image, essentially, one part of the image. The eye, part of the nose, well, and this numbers, so corners, round parts, and stuff like that. So this will essentially allow your model to learn a different filter, a different kind of plane for each image. Okay? And here what it's going to do is kernel size as well is going to be 2 by 2. So we're going to kind of do we're going to go with convolution across the image as well, and take the 2 by 2 image or 2 by 2 cell and reduce it down to 1. Okay? I'm going to use the ReLU activation, and I'm just putting the input shape as 28 by 28. Really important that we're doing this combo 1. It is a one-dimensional, or so it's black and white, so there's only one channel, one color channel, black and white, but normally with convolutions, we have 3, red, green, blue, and so you would normally be putting 3 here, right? And so this is the Z dimension. You can kind of think of the filters as creating another Z dimension from our images, but not necessarily exactly the same in the same dimension. So this is creating another set. So this is just signifying that we have a Z dimension of 1. There's not 3 channels of color. There's 1 channel of color. And then this filter kind of creates 16 images on top of each other as it goes through the network. Okay. So then we do another convolutional layer here. We're going to max pool this, reduce kind of it down 2 by 2. It usually does help our images. Usually this works the same as the sharpen on your photo editor on your phone. It basically makes things clear. And so for the same reason that sharpen makes things clear on your phone, pooling it and just taking the maximum pixel of the 2 by 2 grid tends to make your photos more crisper and will tend to make your network improve as well. I find the average pooling is better to use with a neural network versus something like with a NLP problem versus computer vision problem. We're going to do a dropout layer, really important just to prevent overfitting. Flatten our 28 by 28 grid, our matrix, and then flatten it, and then put a dense layer, and then predict into 10 classes. So I'm doing the softmax activation. To compile this, we're going to do loss of categorical cross entropy. And the reason being is because we are putting in a one hot encoded vector. If it was just one column of data and we didn't do the one hot encoding, it would be sparse categorical cross entropy. Here we're going to do an optimizer atom, and we're going to ask for the 8 accuracy metric. Okay, so I fit this model, images, labels, epochs 30, and validation split 0.2. Okay, so splitting up the data, we get 2.96 accuracy on this data set. So I'm going to, when I look at the training history, I'm going to look at the, I'm sorry, just noticing as well, we're saving the loss and the accuracy from model plot evaluate, and we'll look at and compare all of them for all the different variations of the model at the very end. pd.options.plotting.backend, Plotly is going to make the underlying engine that makes pandas plot based on Plotly, which is this 3D interaction, which is truthfully I find it quite nice to inspect the training history just to see like, oh, right here was the best one. So it's actually at 25 classes. So it was much easier to understand and see with or just versus the standard pandas block. We're still going to use pandas plot to make this. So I'm going to put into a data frame. I'm going to put in a dictionary that I'm creating on the fly. Okay, so what I'm going to do is from the h.history, when I get the history argument right here, h.history, I'm going to be selecting out one at a time. So I'm going to select the accuracy one time, and I'm going to put that into a dictionary with accuracy being key, and then validation accuracy. I'm putting in a list, essentially what this works out to be, of the validation accuracy. Bring that into one data frame. I'm going to then data frame dot plot, plot dot line, and I'm just setting the kind of height and width here. And I'm using the plot, I'm not saying kind equals line, I'm going dot line to use this line, the specific line plotting function, which will allow you to pass arguments that are specific to Plotly, like the height and width arguments. Okay. And I'm going to do, and I'm assigning this to fig. I'm going to go fig.update underscore layout, giving it a title, and giving it the margin dictionary to control kind of the engine. It is different than a plotting engine based on Matplotlib, but it's not super hard once you know what you're doing. And so then we get the next plot, and we can inspect it quite easily as well. So getting into kind of the variation, one of the common variations of this network, so before and the one up above, we had the 2 convolutional layers right next to each other. This one we're going to do convolution max pooling, convolution max pooling. So really what we're doing different than the variation here is we're adding in an extra max pooling. This could potentially help speed up your network. I'd say mixed, and sometimes I've found that this works, sometimes I haven't. So I wanted to bring it up. I think it's really good and important to know because it's a good place to start even because it will make your training much faster. But this is one of the potential ways that we can alter this by adding an extra max pooling layer in between the 2 convolution layers. Okay. Another common architecture that we do, and just kind of looking at the training history again, another common architecture that we do, I shouldn't say common. Another thing that we can do, just noticing here that really we have our 2 convolution, we have our convolution block, we flatten it, and then we do the dense, kind of our standard dense layer. I think studies have found that the dense layer after convolution tends to help. I have tried and I've found kind of sometimes really good success, sometimes not so much. You have to train it for a really long time. And I didn't necessarily do that enough here, but using instead of a dense layer, using a recurrent. So we just have to reshape this. I'm just going to reshape this really again, just adding this extra comma one, because really we're getting a flat vector, but really what we need to do is add that one extra dimension for the recurrent layer, as well as the convolution layer. We need that extra z dimension for both of those to work. So really what we're doing is we're saying comma one, really just adding that extra dimension right there. And then here what we're going to do is put it into a simple RNN. Okay, and train it on for a long time as well. Not too long. I think you're going to train this one for longer. And you can see here, starting to see a decreasing one. Really not as good of performing as the other ones, but I don't want that to make you stray away from it. It does take a lot longer to train. And it might be that we just need a lot more samples to make this train as well. But recurrent layers, it can work well in this situation, so I wanted to bring that up. Definitely give it a try. It will take a lot longer to train, but it can work really, really well. After even something as complicated as the VGG, and then maybe putting a recurrent layer down here. So the VGG, I just wanted to kind of show this out, and really it's not anything super more complicated. This is a very famous model style for a very long time. And really what we're doing, there's nothing really super complex here. We're doing the two convolution layers, max pooling, and then drop. Two convolution layers, max pooling, dropout, and then two convolution, max pooling, drop. We can maybe add another one after this. I would say probably not going to help too much at that point, but this is kind of the classic VGG style network. So nothing really super complicated here. We're just adding three convolution blocks separated by dropout layer and also max pooling. So getting a little bit more complicated, you will find that this is a model that you can just train for a long, long time, and it tends to just keep getting better and better and better. So this is another one, especially with the recurrent layer here down at the end instead of the dense layer, it can just go on kind of forever. So it can just keep getting better. So it's a really good network. It does take a really long time to train, and so something to be conscious of. So going through that, and then just comparing the accuracies at the end of this course. I put all the accuracies that I collected, the names of the models, into a dictionary, and then put that dictionary into a data frame. Even the accuracy, you can actually see here, sometimes simple is better. This is a very simple data set. The MNest kind of classically, just almost unbelievably simple for computer vision. You can actually see here that just the classic one block of the convolutional layers to be the best in the situation. I would say straight away, take that with a word of caution. It's a very small data set. Certainly not all of the MNest images. And then here, I also want to kind of caution you not to take too much into this. The recurrent layer, it didn't do very well. We didn't train it very long, and it would be interesting to see if we train this for 100 epochs or 200 epochs with the recurrent layer with it. The one thing is just to highlight, we did very well with just a very simple network. We might be able to do better with a recurrent afterwards, but is it worth spending the extra day or so to train it? So it's going to be the bang for buck in terms of how much time it takes to train your network. Okay, and then you can see the VVG as well. That is something that likely we might see or we would likely see this get better than the simple convolutional network, but we need to kind of train this for a long time. Okay? But the VVG and the recurrent in a convolutional network, they both can be very good architectures in this simple form. So thank you very much for joining me today, and I will see you for the next lesson.